Zach, over to you.
Great, just confirm you can hear me and that my screen is sharing.
Yes, yeah.
Excellent. Okay, so great. Thanks a lot. Yeah, excited to be here. Unfortunately, I wish I was there in person rather than virtually, but that's the way things are, unfortunately. Looking forward to next year when we'll hopefully be back together. So yeah, I'm talking about OSeMOSYS Global, an open source, open data energy system model generator for the full globe. I want to acknowledge that I'm doing this with my team here in Simon Fraser University, but also with Dr. Abhishek Shivakumar with the United Nations Development Program and Martin Brinkerink from the Marie Center in University College Cork. So the three of us got together and realized that there was a gap in the modeling literature, and I'll talk about that in a second. So, but before I get going, I just want to quickly acknowledge that I'm coming to you today from the traditional and unceded territories of the Kanaquam, Squamish, and Salish speaking people. And so just want to acknowledge that I'm really privileged to be able to live and work on this land and enjoy the beautiful environment that we're in here. And that's, I'm in British Columbia in Burnaby, just outside of Vancouver here is where I'm coming to you from. So OSeMOSYS Global, I'm talking to a group of people who know a lot about energy system models, so I'm not going to go into the details of how energy system models work or any of that sort of stuff. But, and hopefully, given the other presentations and the knowledge in the Zoom room, people are aware that energy system models are a key tool in addressing our climate challenges. Being able to look at the big system picture and evaluate how these different pathways are going to happen, how they're going to work, requires these analysis tools to be able to make effective decisions. And one of the things we realized as we were talking about various different things is that most of the existing global energy system models are not fully open. There's a bunch of different analyses out there, and people have made global models that do the globe, and so but they're not fully open. So there's a transparency and repeatability and barrier to entry there for people who are trying to do analysis. And so the fully open part is the first piece. The second piece is expanded spatial detail. Some of the global models are, well, there's one region in the whole globe. Some are a little more detailed, but we believe that we might be going for the most spatially detailed global model generator here. And then it's also a full energy system model. A lot of the models that exist out there are focused on electricity or other specific energy sectors. And this is really looking at a full energy system model. Open source, open data, built on the OSeMOSYS model that I'm sure a bunch of you know about already. So this is sort of the diagram here. We have the Plexos World 2015 data set, and that goes into a series of different Python scripts that then go into this OTool, which allows us to convert some of the data and then into OSeMOSYS. I see the question on geographic granularity, and we will get to that. So, but great question, definitely something really important. So that's the motivation, is that the granularity and the system model, it's the full energy model, and open source and open data structure for that. So conceptual approach, filling that gap, is we're really doing it using Python from input scripts all the way through a fully functional solvable model with OSeMOSYS, including visualization scripts at the end, and all the pieces in between. We'll also be doing this in terms of making it open, or making it, we're using Snakemake to adjust things. So, or to keep I'm sorry, I got off track there. Brain's not working properly. So yeah, so it's a series of Python scripts, customizable. So the time space content, the specific countries and regions to include can be customized. We can adjust the demand projections, and these are all separate scripts that can be run to detail each different piece. So rather than having to recreate a model from scratch, we can go in and change the way this specific script adjusts these different pieces. So its full tool chain is built in Python. The raw input data, which the Plexos World Open Dataset, is fully open source. all the Python scripts are open source and openly licensed and will be available on GitHub. And so that whole system from input data all the way through to osmosis model, it will be available and free to use once we get all the pieces together. Most of it's mostly working. There's a few little bugs and things. So we do have some results coming up later in the presentation as well. As with any modeling structure, we need to follow specific conventions so that the whole system works together very well. So we have a naming convention, which allows us to define sort of the sector, the specific technology, and then the region, or this is actually sort of, the region is really, at this point, pretty much country, and then subregions. So we might have states in certain areas or regions in certain countries that we want to include. And then we have a number so that we can have multiple CSPs in a given region to allow that to work and structure that really nicely. So consistent, clear naming convention so that everything in the system works. And so when you get, if you're adjusting one script, you're not having to deal with different naming conventions or some random conventions that aren't, so that makes it easier to build the whole system and put things together really effectively. International trade was something that we had to think about. And so this is just an example of one of the, and there's many diagrams like this showing how the different pieces of the model connect together. But one of the pieces was how do we represent international trade? And what we've done with that is we've got this coal mine, for example. This is coal between India and China trade. So there's a coal mine, and in the one mode, it can go directly into the power plant in that same region. But in the second mode, it gets exported into this international coal market. And then that international coal market then can go into these power plants in a different mode. And so the plants can work with either local or regional. And so if there's regional restrictions on the amount of a technology in coal, for example, in this case, we can use that to, we can show how that fits together and how those pieces fit together. So this is just one example, and obviously a global model, there's lots of the diagrams like this. I'm not going to show all of them because I have only 15 minutes. But this is an example of how we've put together the pieces. So for power transmission in each region, we've got a little diagram like this. And so all those different diagrams, and if we were trying to represent the whole diagram for the whole model, it wouldn't be visible on the screen, but we have lots of these pieces showing how all the pieces fit together. I talked about Snakemake earlier. I'm not sure how many people would be familiar with Snakemake, but Snakemake is a tool that allows you to take a series of scripts and change it based on input changes. It will only update the required output changes, and it keeps the whole system, it runs the whole system and makes sure that all your files are updated as required. And so we've used Snakemake to basically put together this full workflow. So we've got the database of raw data, and then the Snakemake will run the different scripts. So power plant data, temporal parameters, costs, demands, and give that in formatted comma separated type values of data, which is ready to deal with the modeling structure. And then Snakemake will run the geographic filter. So because it's a model generator, we can generate the whole globe, or we can generate specific pieces of that as we see fit. And then there's a check to make sure that everything's correct. We use OTool, which is a tool to make it a model compatible file. And then we use the OSeMOSYS model to actually solve it. And then we run some visualizations and get some graphs out the end. And so this whole process really is one command with Snakemake to say, Snakemake, run the model, and it will run that whole structure. And so it's really easy to configure. We have a configuration file, which allows us to define how the different pieces fit together. So as part of this process, and let me just go back one slide. As part of this process here, this first sort of set of blue Python scripts, one of the things is as we do that, we want to do some verification on our actual input data. And so one example is residual capacity here. And here's the residual capacity for a given country. And I don't actually off the top of my head know what country this is. And so there's some hydro, some uranium, some solar PV. And so this residual capacity plot, it's an example of where we might actually say, well, is this actually right? Because you can see in 2025, almost everything retires in that 1 year. Well, that's actually unlikely to happen. We've got sort of 5 gigawatts of CCG power here, and we have that all disappearing in 1 year. That's unlikely. There's probably going to be some tapering off. And so that's an example of where we will go in and check the data and check if our commissioning dates for these different plants make sense, so that we get more of a reasonable residual capacity coming off that system. And so there's these checks in the process as well, where we can see how the different pieces fit together. In terms of demand projections, again, here's a graph that shows the correlation between the electricity demand and the GDP, and the electricity demand and the urban population percent, so the percent of urban population. And this is used to sort of check, are we getting reasonable correlations out? And it makes sense that as the GDP goes up, the energy use goes up, and as urban population goes up, that goes up as well. And so this is a way to just check, make sure that the countries are making sense, that we don't have any negatives. So if there's a population decline in a country, you might actually get a drop in demand. And so we want to make sure that we're sort of checking those different pieces. And so this is all really looking at how that data fits together. Okay, so now spatial representation. Here is I think it's 230 plus specific regions that can be represented in the model. And so some areas like Canada here in the United States have definitely multiple subregions. And then some areas, it's really by country. A lot of areas, it's really by country. We break down China into a lot of different pieces. And this is based on the work by Brinkrink et al. In 2021 in terms of the data gathering that they did for that data set. So that's the spatial representation we have in the model. And so that's the overview of sort of the model structure and how it all fits together. So now let's give an example of what we've done with this. And so one of the things we did is this Gulf Undersea India interconnection. So there's discussion in terms of using solar in the Gulf here. I hope you can see my pointer. I'm pointing at the Persian Gulf area, sort of the Oman area, and India, and sort of using an interconnection across the Gulf there, across the ocean, to connect to India to supply. So basically what we're doing there is we're trying to supply solar energy from the Gulf to India. And there's a really nice advantage there in terms of the time zones, because when it's really sunny in the Gulf, we can transmit that power to India when they have their peak dinner time demand. So there's a really nice synergy there with piecing those pieces together. And so power demand by country, we can see that India, being the biggest country in that area, in those different countries that are connected, has by far the largest power demand. And here's the sort of countries that we have in the model itself. And so there's this big chunk that's India, but we know that the Gulf has lots of sunlight and might be able to provide solar power to the area there. And then so NEO capacity, we can see that the model at this point in 2025 starts significantly installing solar to try and take advantage of that. And that's once we get that link going, we get that advantage of having that solar in the one area and the demand, that synergy happening in the model. And I don't have the details of how all the different pieces work. I don't have time to go into that in a lot of detail, but that's sort of the general idea of how that is working in this model. And so total generation capacity, so that was the NEO capacity that was installed. And here's the total generation capacity. And we can see that there's a massive build out of solar as we go here. There's a little bit of wind, there's a decent amount of wind as well, but we're basically building out a lot of solar to try and use the Gulf states' nice supply during the peak demand in India. And that's complemented with some natural gas and some wind. And I think the natural gas and wind is mostly being installed in India to sort of balance the system. And the peak solar really does that peak demand. And there's a really nice synergy there.
Only 1 minute left.
Okay, that's perfect. I have like 2.5 slides left, so we're in good shape. So you can see here that this demand, the peak demand here, is being met by the solar quite significantly. And that is that piece that I was talking about, that we've got this solar at really useful times in India, while the Gulf is not necessarily having that demand in the middle of their day. And so you've got that synergy happening there. So to conclude, we're building and have built a fully open source, fully open data model generator that allows for scenario exploration of alternate global power system configurations, impact of increased and decreased cross-border interconnections. So how do we connect those pieces together? Regional studies in key locations allow us to focus on specific questions. So load shifting in Southeast Asia, which I already talked about, potentially hydro in sub-Saharan Africa, solar in India, wind in the North Sea. So there we can do those regional studies. We can also run the model globally. Model code, workflow data, and visualization dashboard are all open source, and they're going to be they're currently on GitHub, but we can publish some of those pieces as we finish up. There's still a few little bugs here and there, but I think actually models always have little bugs here and there, so that's probably not just unique to this model. But so we're squashing bugs as we go and getting that done as fast as we can. Thanks.
Thank you very much for your presentation. I tend to agree with you. You know, model development is a never-ending activity. There are a few questions to you in the chat. Some of them you probably have answered already. Do you want to go through them one by one and just? Sure.
Yeah. So I'll ignore the question for Carlos. That's still in there. Geographic granularity, I think I did cover with the 230 regions there. And so, yeah, and as I said, you can cut that in any way, shape, or form that you want. You can define which countries do you mean. By open model, open equations, so open tool sets, open source code. So the model can be run fully open. You can download all the different pieces, and they're all open source, openly licensed pieces. So OSeMOSYS is an openly licensed model. The solvers for OSeMOSYS are openly available. We sometimes use Cplex because it's a little faster than some of the open source modeling, but there's open source tools that work quite well.
So I guess it's open in the sense of the open source initiative, right?
Yes, yeah. In terms of the free open software type version, exactly. I see a comment about Markle Times being transparent, but I'm not sure exactly what that question is. And then question about sectoral power demand, and mostly focusing on supply and developing hourly profiles. So modeling sectoral power demand, yeah, it is both in electricity, so looking at the power demand, but also the other energy demand. So looking at natural gas. So if we have a natural gas power plant in an area that doesn't have a lot of natural gas, we're looking at the energy flows there as well. So it's not just power, but it's full energy. And focused on supply. So the hourly profiles for demand, we have existing hourly profiles that we are using. We're not developing new hourly profiles, but we are using hourly profiles and then choosing that. The time slicing is also customizable in this model. And so depending on what you're looking at, you can look at, do you want to do the full time horizon? So a long-term model with more time slicing, or do you want to do a shorter term, more detailed model with different profiles? So that's customizable. And since it's open source, you can change those as you wish. And then, yeah, someone says about India's link towards some of the other Asian countries due to land connections and geopolitical issues. Absolutely. That work was actually part of a project that we were asked to investigate with the modeling because a specific group was interested in that link to the Gulf. There's definitely geopolitical issues with any links that go between countries. And as a modeler, I try not to get into the geopolitics entirely, but I try and look at how to solve the challenge that we have. And then the politicians have to go figure out, can we actually run the line in those places? But great questions. Thank you, everyone, for those questions.
Thank you very much, Teko. To be honest, I also have one question, but I'll just post it in the chat.
Okay.